Welcome to class. In this video, we would consider the concept of poles, singularities, and extend into the concept of residue. Now, it is very, very important to understand where and what these concepts are because they form the basis for what residue is, and residue will be very, very instrumental in us being able to integrate functions within regions for complex analysis, whether it's the semicircular contour or is it within the unit circle. We would only be able to integrate when we have a sound understanding of how residue work. So before we do so, we will talk about poles, we'll talk about singularities, and we would talk about the relationship they have. Now, as always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, we'll start off with poles. When we refer to something as a pole, we simply talk about the effect and to the degree of the effect it has on that function not being continuous at that point. Now, what exactly does that mean? Let us give ourselves a rigorous definition. We say for a fact that a point Here we go. So we say for a pole, a point z0 is called a pole of order n if it fails to be continuous, if the function f of z fails to be continuous at z0, but the limit as z tends to z0 of z minus z0 raised to the power of n f of z exists. What this means is z0 will be a pole if when you find the limit at z tends to that pole, the function is indeed the function fails to be continuous, which means the limit does not exist. However, when you multiply the function by the exact factor of that pole, and then you take the limit again, the limit exists. Now, what exactly does it mean? It means that these poles are simply just points of discontinuities to which you can find that makes those functions undefined. Now, a good example and something very, very simple to work with is if we have a function which is equal to 1 divided by z minus 1 squared z plus 1. Now, in this case, we will notice that for this function to be undefined, we just need to set the denominator to be equal to 0. Now, if we set the denominator to be equal to 0, right, we do not want to spend too much time solving, but splitting this, we can see immediately that z equal to 1 of order 2 is a pole, which is z equal to 1 is a value that makes this equal 0, and then z equal to minus 1 is also a value that makes this equal to 0. Now, when we say of order 2, what do we mean? It means that for the factor z equal to 1, which is z minus 1, the degree of operation of that factor is 2. So you have z minus 1 squared here, which means there's going to be twice the result for z equal to 1. Here you have z plus 1 raised to the power of 1. So it means z equal to minus 1 is going to be a pole of order 1 because it's linear. It's a linear factor. Now, these are very, very important to consider. Now, of course, for order 1, we can also term that as a simple pole. And then for order 2, we can also term that as a double pole, right? For order 3, we also call it a triple pole. But then the naming, of course, just talks more deeply on simple or shorter scaled orders before it gets too complicated. But in most cases, you can just refer them as poles of order n, where n can be 1, 2, 3, and so on and so forth. So this is what a pole is. You would recall that in the last few videos where we talked about the Laurent series and we talked about finding something we called poles, which are the points of discontinuities where we had to set the denominator to 0, you would see that those poles exactly were of this nature. Most of the poles we found in those questions were simple poles, right? But then you could also have poles of double. You could also have poles of order 2, 3, 4 above, and you can still find their series representation, of course. Now that we have this, let's move on to yet another important concept that we need to know about, and that is the concept of the removable singularity. Now, for the removable singularity, what exactly does it mean? Let us see. So, a removable singularity. We say this is a point z naught such that f of z fails to be continuous at z naught, which means if you were to evaluate at z naught, exactly at z naught, the function will fail to be continuous, right? Which means the value of the function will be undefined. However, when you take the limit of the function as it tends to that removable singularity, the limit exists. Now, how exactly would that happen? That would happen, of course, due to the existence of concepts like the L'Hopital's rule, which is something very, very interesting to keep around or to understand. Now, it also means that we could say that the function is going to be undefined at z naught, but the limit as it tends to z naught, f of z exists. Now, what exactly does that mean, or how exactly can we paint that picture? We can simply talk about an example of the form f of z equals sine z divided by z. Now, if we have this representation, we would notice that at z equal to 0, f of z will be undefined, right? F of z will be undefined. Now, if f of z is undefined at that point, or of course, if you want to be more specific, you could say that f of z would be 0 divided by 0. Now, if this is what happens at z equal to 0, what then would be the value of the limit? We notice that if we take the limit as z tends to 0 of sine z over z by the L'Hopital's rule, because we have f of z being equal to 0 over 0, so definitely it qualifies to be used or for the L'Hopital's rule to be evaluated on it. Then at that point, we can differentiate the numerator to have cos z, and we can differentiate the denominator to have 1, such that if we then reevaluate the limit as z tends to 0, we will now have 1 as our answer. And then we can see that the limit does in fact exist. So that is why we call it a removable singularity, which means even though the function becomes undefined at that point, right, it is possible for us to extract that singularity out, and the function now becomes continuous over every other place in the interval. This is very, very important. So removable singularities exist, especially for functions to which, via the usefulness of the L'Hopital's rule, the limit of the function exists. So these are very, very important to showcase or to keep in mind. Right? Now, based off this representation, we can look at several other kinds of um, um, poles or singularities we have. But more importantly, we can look at one very, very interesting kind of singularity, which is the essential singularity. There we go. So we have ourselves an essential singularity. I will say that a pole z naught of a function f of z is an essential singularity if its order is infinite. Now, what exactly does that mean? It means that for this function, when we evaluate at that point, right, it makes the function undefined, yes, but then the order of that pole, because if since it was making the function undefined, we could call it a pole, but the order of that pole is not a finite value, which means the order continues to increase as you proceed. Now, what kind of functions can we have? We could have f of z being equal to e raised to power 1 over z divided by z. Now, in the case of this, what do we notice? We realize that based off the fact that we can write the Taylor series of e raised to power 1 over z as 1 plus 1 over z plus 1 over 2 pi z squared plus 1 over 3 pi z cubed and so on. And all of this will be divided by z. We immediately see that we can represent this, or we can rewrite this immediately as 1 over z plus 1 over z squared plus 1 over 2 factorial z cubed plus 1 over 3 factorial z raised to the power of 4, and it continues. The power of z continues to rise, which means if we were to take the LCM of this sum, the LCM would be the largest power of z, would be based off the largest power of z, because the LCM has to be able to divide all of them. And the largest power of z is infinite, because we do not even know when or where this series will end. So in this case, z equal to 0 will have an order of an infinite power, or would have an infinite order. So in that case, z equal to 0 will be termed as an essential singularity. So here we go. So this exactly shows us exactly what it means when we talk about poles and singularities. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. And if you have any questions or notices or opinions, you can let me know in the comments.